plant-based Thanksgiving. They don't have the actual bone. So the wishing bone experiment. It's the wishing bone experiment. Okay, so we break the wishbone in half. We don't look at our pieces. One has a big piece, one has a small piece. I go to Andromeda. I look at mine, and I find out I have the big piece. I instantly know you have the small piece. Now, there's nothing surprising about that because it was established at the table which one had the big piece and which one had the small piece.
Right.
Now, quantum entanglement is much weirder. It says we break the wishing bone, and it's at simultaneously in a state where I have the small piece, you have the big piece, and I have the big piece, you have the small piece. It has not yet been determined.
And by any entity.
No, it is completely in what we call a superposition, but it has to match. We can't both have the small piece, and we can't both have the big piece.
That's why the two states are not, we both have the big piece. It's I big, you little, you big, I'm little.
Right.
Those are two states.
Exactly. But they have to match because they have to fit together to make the original wishing bone.
Right.
But it's not actually determined who has the big piece yet. And quantum mechanics allows for this.
We can't know. Is there some higher dimension? Is there God who would know?
Well, if you're a real adherent to quantum mechanics, you would say that you've disproven the possibility of omniscient being. Because no, it is not established. In some sense, when we, in our conventional thinking, are accustomed to thinking certain things are real, what's real is the piece of the chicken bone is real. We're sure of it. But it's not, in some sense, real. What's real is the probability. That's real and that's determined. And that is absolutely deterministic and can be predicted, the probability. But the existence of the pieces of bone themselves are not yet actualized. They don't actually have a concrete existence.
So you're saying you and I are entangled with each other.
Right. And we have to be entangled. Right. We have to be entangled because we can't both have the small piece because that's not cool. So we have to be entangled in such a way that we fit together correctly to make the original wishing bone. So I can have the small piece, you could have the big piece, I could have the big piece, you could have the small piece. But we don't know which one it is yet. It's not just that we don't know, it's that it doesn't actually assume a precise state yet.
Okay, so when does it assume that precise state? Because at some point, this can't just be potential. At some point, there has to be a realization of who has what piece. So when does that happen, and how do we determine that, and how do we observe that? So
superpositions are very delicate. So when they do it, as you were saying, Neil, like in the laboratory, everyone's trying to do this in the lab, and it's very, very, very delicate. You have to have systems that are not disrupted or disturbed in any way. So there was this sort of mystique that once I went to Andromeda and I looked at it, that the act of my conscious looking forced it to assume a certain state. And that's not really quite right. What happened was just all the molecules in my body and the air that I'm breathing and the room, all of these things destroy the delicate superposition. They knock it about. Imagine, a pencil standing on its end. So if you go and clumsily look at it, you knock it over. But it doesn't have to do with your consciousness. It's just the interaction of all the particles and all the molecules and all those things that make it impossible for it to maintain this delicate state of standing on its point.
Okay, so now the state becomes actualized in front of you.
Yeah, so now I look, and I know for sure I've got the big piece. I won. But what happened is I somehow seemingly forced, faster than the speed of light, from Andromeda to the Earth, instantaneously forced your state to also assume a precise state.
Because you can't know that without me also knowing my state.
Right.
Well, I can know it. I can look at it and know it, and I instantaneously know you have the smaller piece of bone, and that's that. But you don't necessarily
whether I've looked yet or not.
That's right. So,
but that's only because the two there has to be that balance of big and small. That's the only reason.
It's right. They have to fit together to make the original wishing bone. Exactly. It can't be that I look at mine and then you also look at yours and we both have a big piece of wishing bone.
All right. So the big question here is, can you encrypt messages this way so that no one can jump in between and capture your secret code that you're trying to communicate from Andromeda to Earth?
Yeah. So funnily enough, I cannot communicate to you faster than the speed of light that I know I have the bigger piece.
But
so
that information was communicated nonetheless.
It was. So you look at your piece and instantaneously you see the small shard, but you don't know that you didn't do it. You don't know that it was you who collapse wave function. And so for me to tell you, I just use fancy language, sorry, collapse wave function, meaning forced it to assume a specific state. For me to tell you, I would still have to send you a mail in the post.
I don't need
send you a signal.
I don't need you to send me a signal because I know.
Yes,
so isn't that communication faster than light?
It is communication faster than light, but neither of us know who was the one who did it.
Exactly, because it's not communication faster than light, it's knowledge faster than light.
I can't communicate faster than light, but I can definitely force that wishing bone to assume a specific state faster than the speed of light. And you could learn about it later. Like I could tell you it was this time in Andromeda when I looked at the bone. I can send you a intergalactic mail in the post and you'll get it and you'll say, oh yeah, it's true. When Janna looked at the bone, I looked at mine a second later.
But if I'm thinking about cryptologists. So can we entangle a sequence of bits, if you will, right? And then you choose bits in a certain way that then collapse my wave function back here. And I say, oh, Janna has the secret rocket formula and it's this.
In principle, yes. I can throw you that information faster than the speed of light. It would be hard to control which information I send to you because I can't know if I'm going to look at which piece it's going to be.
Okay, but let's say you look at 1, 7, 9, and 11.
Yeah.
Of the 12 particles that we entangled.
Yeah.
Okay. And that's a decision you make. And I will know. And I look up in a code and I say, forget that it's big piece, little piece. Forget that it's big chicken, little chicken. All right. I look at a code and say, if she does 1, 3, 7, 9, that means she's safe in Normandy with the rocket formula.
Yeah. You sort of can do it. The problem is when you look at your piece, you don't know if you're the one who forced it to assume a position or if I was.
Oh.
Wow.
Oh.
But there's probably some clever way around it. But let's say so it's not as though you can look at your particle and wait to see it.
Right. That's what I was asking.
Because then you could do exactly what you're saying.
Right.
You could encrypt a message. I do 4, 7, 2, 9, and you look at your book, and that means, I'm safe on the shores. But once you're looking at the thing, it's not like you can watch it come out of entanglement into the state. By looking at it, you no longer know if you're the one who forced it or I was.
Wow.
Yeah.
So it's not a good way to break up with somebody, is what you're saying.
Do you have a good way of breaking up?
Yeah,
it's not me, it's you. I mean, it's not you, it's me. I don't know.
Exactly.
We don't know who broke up with who once the message is looked at. Wow.
So Janna, does this relate to quantum computing at all?
I was just about to say, absolutely. So quantum computing uses entanglement and, in a very delicate way. And the arguments are that the computational power of a quantum computer are incredibly vaster than a classical computer. And there's a lot of progress made on quantum computing. Not all of which I understand. A lot of it's some pretty wild stuff. And it's very forefront stuff. It's changing every day.
But it's exploiting quantum entanglement as one of the quantum
absolutely
elements that are being attacked.
Yes.
Is what you're...
Yes, absolutely. Okay. Yeah.
Right. So now, can you tell me the difference between the entanglement and tunneling, or are they the same?
Yeah, it's an interesting question. They're both quantum mechanical phenomena.
Yeah.
And they're related, but they're not exactly the same. So quantum entanglement talks about, one thing that split and had to assume complementary states so that it could go back together again in the right combination. But I could have a single particle inside a box, and because that particle is no more real than the pieces of the wishing bone, it has some probability of being on the other side. There's just some
outside the box,
outside the wall, on the other side of the wall. There's just some chance that it's there. You have to stop thinking of it as a billiard ball that actually exists all the time and is there. You have to start thinking of it as something that has a probability of being somewhere, has a probability of moving.
So what you're saying is the particle in the
exist.
Which box is a convenient way to start thinking about it, but the particle actually exists in a space, not only in the box, but outside the box with a probability.
I'm going to tell you what I just heard from a non-astrophysics, you just told me that nothing is real.
On that
note, no, seriously, you just basically said nothing's real. Like, seriously, oh God.
So here's an example also. So tunneling is the idea that there's some probability it's going to end up outside the box. There is some probability that I will just pass through the wall unharmed. It's very, 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 very small. But so here's another way of thinking about it. Like there's atoms where you have the nucleus, and then you have these regions where an electron can occupy. And one electron can occupy like a lobe here and a lobe here. And it never, never, never goes between. Never. But it's still one electron. And the probability of finding it here is some probability, and the probability of finding it here is some probability. And you do the experiment over and over again, and sometimes the electron's here, and sometimes it's there. It does not make its way over in the ordinary billiard ball sense.
Wow.
Chuck, I love your face now.
I got to help out Chuck.
That is so...
I got to help out Chuck. So Chuck, and Janna, correct me if I'm not saying this right. These quantum forces and phenomenon are particularly manifest at matter on its smallest scales. But as you start collecting matter together macroscopically, these effects end up, I don't know, canceling is not the right word. They end up being...
the probabilities go way down.
They go way down. So what would happen is, Chuck, for you to end up on the other side of the wall, all of your atoms would have to sort of have manifest that probability simultaneously. And that is an astronomically low likelihood. Did I get it right, Jen?
Yeah. Absolutely. And also like things like quantum entanglement are again very, very delicate. And so when I shine a light on it and I bombard it with photons, or I like try to look at it, or I grab it, or I do whatever I need to do to make the observation, it's not about my mind, my consciousness. It's simply about the interaction of my apparatus and that thing. And I just break it to some extent. I break the entanglement.
So then how can you ever see it? If you can't put light on it to see it, how do you ever see it?
Well, it's a really interesting question. It's really a probabilistic experiment. You do it over and over again, and you measure the probabilities, and it's different than the probabilities that we would have if it was the classical experiment at the dinner table where we broke the wishing bone. You can actually measure with large numbers that it's a different, it conforms to quantum mechanics and not to the dinner table experiment.
Wow.
So I think Chuck has just lost a week of sleep there.
Oh my God.
All right, we got to land this plane. So Janna, as always, thanks for being a friend of Star Talk.
Always. I love being here.
Always great to have you.
I'm hoping we'll all be together in person soon enough. Miss you guys.
Star Talk in the coronavirus. Chuck, always good to have you.
Definitely.
This is Neil deGrasse Tyson, as always, serving as your personal astrophysicist and bidding you to keep looking up.